As a society, we are transitioning to a networked information era. Communication networks are key enablers of numerous societal services, including commerce, governance, transportation, or health. The related traffic growth and tight performance requirements put great strain on communication infrastructure. Optical fiber networks, with their large capacity, low loss, and low power consumption, are the most sustainable solution capable of satisfying these needs. As our societies become more and more digitized, the lack of trust and security in cyberspace can have detrimental effects on the opportunities brought forward by the digital evolution. To avoid this, advanced approaches are needed to enhance security at all network layers. While many security breaches never get reported outside of an organization, numerous instances of attacks have been made public. Some of them caused widespread damage and led to formal investigations. In the face of this, cybersecurity is becoming an integral part of national defense systems. Optical networks are not exempt from the evolving security threat landscape and are vulnerable to various attacks targeting disruption at the physical layer. Attacks can be performed by gaining access to the fiber plant in unprotected premises. Well-known monitoring techniques can be abused to create temporary couplers by bending the fiber and allowing the light to leak out or be injected in the fiber. Jamming attacks, in which a harmful optical signal is inserted in the fiber, are deemed one of the most harmful attack techniques. For in-band jamming, such signal is at the same wavelength as the targeted user signal and adds unfilterable noise to it. For out-of-band jamming, the inserted harmful signal does not overlap with the spectrum of user channels, but degrades their quality by aggravating nonlinear effects in the fiber and reducing the optical amplifier gain. Other methods of attacks do not require physically intruding the fiber to disrupt service. In polarization scrambling, fiber is squeezed at a high frequency. When this polarization modulation is too fast, it results in transmission errors. To improve physical layer security in optical networks, a cognitive security management framework is required. Such framework needs to include methods for prevention, detection, and reaction to attacks. Monitoring of attacks is in the focus of this work. It requires deep knowledge about the signatures of various attack methods. Because different attacks affect optical signal parameters in different ways, complex attack effects are difficult to model and identify. In our study, we use experimental data obtained by subjecting a telecom operator's network testbed to various physical layer attack techniques. We then apply machine learning for a deep analysis of the experimental data. Supervised learning is used to perform fine granular identification of the attack type and intensity upon training on the labeled data. Unsupervised learning is used to cope with emerging threats by detecting presence of attacks even when they are previously unseen. Apart from being aware of the presence of an attack, the physical location of the breach must also be determined for quick and efficient recovery. Therefore, we identify the scope of different attack techniques and model them with binary words called attack syndromes. Attack syndromes for different attack methods and their sources are stored and compared with the actual security statuses of the connections. To acquire representative experimental data, we use Telecom Italia's testbed equipped with 6 reconfigurable optical add-drop multiplexers and 10 fiber links. The coherent receivers collect a rich optical performance dataset and report values and statistics on 12 different parameters to the network management system. In-band, out-of-band jamming, and polarization scrambling attacks were performed, each at a weak and strong intensity. In total, data from 14 different security regimes were collected. 1,440 samples were harvested for each regime by obtaining 1 sample per minute over a period of 24 hours. This makes it the largest reported experimental dataset related to optical network security. Our demonstrator showcases how the modules for attack detection and localization can be integrated into the network management system. It emulates the transceivers using the samples collected in the experiments. By leveraging on this data, the demonstrator allows selecting from a broad range of attack scenarios. Attack technique, its intensity, and location can be dynamically chosen. The monitoring server periodically polls the transceivers and dispatches the received optical performance data for attack diagnostics. Attack detection can be performed by choosing between supervised or unsupervised learning, and attack localization can be enabled on demand. For a selected setup, the system visualizes the output of the selected machine learning algorithm for attack detection and the attack localization results. When supervised learning is used, probabilities of different attack statuses are calculated for each light path using an artificial neural network. These probabilities change dynamically when an attack is injected. When unsupervised learning is applied, the dbScan algorithm clusters the samples and interprets outliers as anomalies caused by attacks. The attack localization module relies on unique attack syndromes to identify the breached link. When attack syndromes are ambiguous, monitoring probes are activated to enable precise attack localization. For some attack techniques, attack syndromes cannot be unique even when additional monitoring probes are set up. This can be resolved with additional checks at intermediate nodes and by defining monitoring schemes that introduce a minimal overhead. The diagnostic data provided by the attack detection and localization modules are visualized by the monitoring system, which provides a rich graphical representation of the network security status. The modules are implemented in the form of containers and use standard open interfaces. They provide holistic, integrated data analytics and enhance optical network security.